Welcome to my channel. My name is Opubo. For those of you new to the channel, I welcome you. And for those returning, I bid you welcome back. Good to have you return. You are well appreciated. As with prior presentations, in this channel I present various ideas and technologies, designs, mostly from the Technology IP Bank of Enhanced Knowledge LLC, often integrated from several other technologies already in the bank and made ready for adoption by the Adoption Brokerage Division. This presentation focuses on polychlorinated biphenyl reactive-decomposition technology. It's part of the conservation economy, the process of utilizing materials that would otherwise be considered waste. The process of recovering materials that would otherwise be considered waste that would now be subject for utilization in some other technology for global wellness and health. So this technology focuses on decomposing a carcinogenic additive chemical to oil base in order to enable utilization of the base discarded oil. The carcinogenic chemical polychlorinated biphenyl was added to oil used in transformers for cooling in the 1960s and could not be disposed of because of the carcinogenic nature of the chemical. Of course, the oils were all removed from the transformers and then they are placed in various containers with the hope of having them disposed of, provided they were able to find some means of destroying the PCB. Attempts of various forms were made to dispose of the oil and the PCB, but the attempts often fell short of outcomes that were deemed safe. One particular method that was somewhat acceptable was that of burning the oil and the PCB in cement kilns. However, even that approach, though yielding about 99.5% destruction, was still found to have residual parts in the smoke as performed. Consequently, the destruction, even in cement kilns, was discontinued, and the contaminated oil stored in underground. In fact, the oils collected from U.S. military bases are currently still stored underground in Delaware and awaiting a safe means of destruction of the PCB. There are possibly other short storages of vast quantities of the PCB contaminated oil. On this reason, an attempt was made in 1987 to develop a means of destruction of the PCB in the oil. A chemical reactor design was developed and under testing for a while when the development effort stopped. Even so, an initial design of a process based on the use of the for adoption reactor design was made in 1987 when the issue was taken head-on as to find a solution. But the development did not get finished for assortment of reasons. Yet, the research effort continued, but with significantly less focus, until recently with the development of newer methods considered to prevail guaranteed hydrogenation of the benzene molecules. Listen, however, for a moment before making a deep dive into the PCB decomposition technology. If you have not as yet subscribed to the channel by simply clicking on the subscribe button below, I implore you to do so. Please click the subscribe button now. The subscription would cause the system to keep you informed by way of notification once the next presentation is published. And also, of course, help me to have consistently more viable presentation to elicit the peace dividend of conservation economy. Now back to the presentation. Few of the improvements of the recent research development. The reactor design then focused on the integration of the earlier and the newer technologies to ensure a virtually guaranteed destruction of the carcinogen and consequentially the utilization of the base oil used in the electrical transformers. The current design is therefore one of the programmable chemical reactor, becoming the model 3 of that class of chemical reactors in the IP bank. The process design also has been much improved, though, with this version resulting from integration, again, with other technologies in the technology IP bank. And the schematics is as shown in the figure. Conceptually, the technology, when fed with the PCB contaminated oil and hydrogen, it ignites reaction between the PCB constituent atoms and the hydrogen atoms, producing hydrogen chloride and hydrocarbons, which are not carcinogenic and can be separated and sold for financial benefits. By design, the technology consists of an electrolyzer, the programmable chemical reactor, cooler condenser, oil decanter, hydrogen reactor, thermosiphon reboiler, distillation system, and flash equilibrium steel, and as always, a controller system. Looking at the schematics, the process appears arranged in 4 columns. In the leftmost column, the equipment at the lower left corner is the thermosiphon reboiler. Above it is the hydrogenation reactor. In the second column to the right is the cooler condenser, and immediately below that is the flash equilibrium steel, below which is the electrolyzer. In the next column, which is the third column from the left, to the top is the oil decanter, and below that is the programmable chemical reactor, the Model 3 of the class of programmable chemical reactors in the IP bank. Finally, at the top right corner are the storage tanks for oil and benzene, if such should exist. And below those is a fractionation distillation system. During operation, water is pumped into the thermosiphon reboiler, where the water boils and produces steam, which flows into the electrolyzer and is broken up into hydrogen and oxygen. The hydrogen flows into the programmable reactor fed at the upper part of the base, and the PCB contaminated oil is also pumped into the programmable reactor at input below the hydrogen pot. The hydrogen atoms react with the chlorine atoms and form hydrogen chloride, and also react with the benzenide carbon atoms and form cyclohexanes and some hydrocarbons. The cyclohexanes and hydrocarbons may nucleate and form bubbles or partially remain dissolved in the oil. The gaseous effluent, which may carry oil vapor, flows into the cooler condenser, while the oil is pumped into the flash equilibrium steel to separate out all dissolved gases. Of course, the flashing process may also cause some of the liquid, the oil, to vaporize. The gases in the flash equilibrium steel is pumped into the cooler condenser also, while the oil is pumped into the decanter and bubbled through water to attract the acid out of the oil. At the surface, when the oil droplet smears into thin film, the remaining acid molecules dissolve into the water. Meanwhile, the surface oil is decanted and pumped into the distillation boiler, which boils it up and sends it into the distillation column for fractionation. The cyclohexanes of the cooler condenser are pumped into the hydrogenation reactor, where any incomplete hydrogenation is completed and some cyclohexanes even hydrogenated into straight-chain hydrocarbons. This time, it can be said that there can be uniform acceptance that there is in fact a technology for the assured destruction of polychlorinated biphenyl, even when dissolved in oil and other benzonoid chemicals that may need to be destroyed for health and wellness. The process engineering materials of construction being mainly steel, the technology is still well suited for the utilization of discarded metal parts and can be readily constructed out of the used process equipment discarded by chemical companies that have shuttered operations in every region, allowing for the elimination of matter that would otherwise be branded as waste. In all, the technology satisfies the characteristics of conservation economy in enabling the recovery of constituents of a recalcitrant chemical, polychlorinated biphenyl, recovery of contaminated oil, and the reuse of abandoned process equipment, resulting in better resource utilization. Then, if interested in licensing this technology, please send an email to me. The email address is put in the pinned link below, as are other useful information. Regarding licensing considerations, there are some notes that should be of interest. The post-processing of the cyclohexane in the hydrogenation reactor was presented on the assumption of a single cyclohexane. However, should more than one cyclohexane or hydrocarbon forms, then there would be the need to deploy gas separation unit operations of the quality of air gas separation unit operation. In effect, the process design should become more expansive than as presented. The design is safe in that it does not allow any direct interaction between the plant operators and the hazardous oil. Besides, because the oil only point of introduction in the plant is in the programmable reactor, that entire operation could be further isolated in a sort of quarantine facility during operations. That option, as such, exists as part of the licensing consideration. On that note, I thank you for being here, and I appreciate your coming to listen and to view the presentation, and hope and expect that you would consider coming back for the rest of the future technology presentations. The fact is, even if you do not adopt a given technology, the contents of some might still change your perspective of society and life. Until the next presentation, I wish you be well.